Section 9.3, testing a claim about a proportion. In the last chapter, we were creating confidence intervals where we took the results of a sample and used it to make an estimate of a population parameter, a true proportion or a true mean. In this chapter, we're taking a sample again, but this time we're using that sample to make a decision about some claim, some initial hypothesis. So for example, a large car dealership claims that the proportion of all car buyers who purchase an extended warranty is 0.6, 60%. This is about all car buyers, so this is a population parameter. An investigative reporter suspects that the true proportion is somewhat lower, so he thinks that it's actually less than 60%. These are both about a parameter. Now we're going to take our sample and use that sample to try to reject this null hypothesis and prove that the investigative reporter suspicions are correct. Now, the first thing that we need to do before we conduct a hypothesis test is check to make sure that the conditions are met. So we have the same conditions that we've been dealing with, randomization and large counts. One tiny thing changes about the large counts. We had done NP and NQ in the previous chapter with confidence intervals, but that had been NP hat and NQ hat because the P hat and Q hat were based on a sample. In these problems, they're going to be based on a population parameter. Now, we don't necessarily know what that is, but we think we know what it is because we think it's whatever our null hypothesis is. So when we do NP, we're using the P from the null hypothesis. Same thing with the Q, all right, 1 minus whatever that null hypothesis value is. So to check our conditions, we're going to make sure that we have a random sample that's less than 10% of the population, and we have values for NP and NQ based on that null hypothesis P, and that both of those are at least 10. This problem was introduced in the last video where we had the manager of a drive-thru who's looking to reduce the proportion of customers who have to wait more than 2 minutes for their order. Historically, it's been 63%. He assigns another worker on to assist with the drive-thru in hopes that it brings it down from 63%. Now, these are both about the population of all customers. And now what we're going to do is look at the results of a sample. So in the text of the problem here, we see that he takes a random sample of 250 drive-thru orders. And in that sample, 141 out of 250 had orders that lasted or took longer than 2 minutes. So this is 56.4%. It's less than 63%. But keep in mind, these results are going to vary. If we took a different sample of 250 orders, we're going to get something different than 56.4%. So does this provide evidence? Is this low enough for us to reject that null hypothesis and conclude that it's a statistically significant difference, that average or that proportion is definitely less than 63% with the new worker? So to start, we'll check our conditions. It notes that this is a random sample of 250 drive-thru orders, and 250 orders is less than 10% of all orders. We want to check our large counts, our NP and NQ, and we're using that P from the null hypothesis, not the P hat from the sample. So we'll use 0.63 and find 250 times 0.63, and the Q is just 1 minus that 0.63. We see that both of those are at least 10, so we're good to go ahead and perform this test. So now we're going to take a closer look at our sample result, our P hat. We have a P hat of 0.564. That's less than the 63% historical proportion of people who have to wait too long for their food. So it's giving us some evidence that this worker is effective in reducing the proportion of people who have to wait too long. However, is it convincing evidence? Is this a result that would be unlikely to happen by chance? Now, that's under the assumption that the null hypothesis is true. So if we made a normal curve centered around that null hypothesis, 0.63 would go right in the middle of this curve. If we looked at 250 orders, sometimes we'll get a little more, sometimes we'll get a little less than 63%. Where would this fall on this curve? How likely would it be? That would be the p-value for this problem. And this is where we start combining different elements of the course into one single problem. So to start, we're going to create a sampling distribution. So in this sampling distribution, we're going to assume that that null hypothesis is true, and the true proportion of people who have to wait too long is actually 63%, which means that 0.63, that null hypothesis, is going to go right in the center of our curve there. The other thing that we need is the standard deviation. And this is a sampling distribution of size 250. That's our sample size. So we're going to use that equation back from chapter 7 when we learned about sampling distributions. We wrote it as radical PQ over N. So we plug in that 0.63, 1 minus that 0.63, sample size on the bottom. That all goes inside a square root, and we get the standard deviation for this curve here. So our normal curve is centered at 63%, and it has a standard deviation of 3.1%. So when it comes to finding a p-value for our p-hat, it really simplifies to just finding a z-score and looking it up in our yellow table. So based on this distribution, where 0.63 is right in the middle, our standard deviation was based on the sample size and this true proportion. Would it be unlikely to get 0.564? You can see that's right here. We're finding the probability of the left tail here because our alternative hypothesis is a left-tailed test. It's less than 63%. So we're going to find a z-score for this. All right, it's written out fully here, but in reality, we're just going to take that 0.564, subtract the 0.63, and divide by that standard deviation that we got on the previous slide. We get a z-score of negative 2.13, and then we look that up in the table. This value, this z-score, is called the standardized test statistic. It's simply a z-score. Now, simply from what we know about z-scores, we can tell that this is unusual. This 56.4% is more than 2 standard deviations from the mean, which means it would be unlikely to occur by chance. That would be evidence against this null hypothesis, leading us to reject it and conclude that it's actually gone down from 63%. And we do essentially the same thing with a p-value. It's just a little more formal. So we have an alpha level for this test, which is 10%. We're going to get our p-value by looking up this z-score in our yellow table, and we end up with a p-value of 0.0166. Because that p-value is less than that alpha level, we're going to reject the null hypothesis. And we always want to use that similar wording where we're saying reject the null hypothesis and the justification because the p-value is less than the alpha level. We're then going to write our second sentence, and the second sentence is always about the alternative hypothesis. In this case, the alternative hypothesis is that p is less than 0.63. If we reject that null hypothesis, we have evidence that this is true. We have convincing evidence that the true proportion of drive-through customers who have to wait more than 2 minutes is now less than 63%. Just a reminder back from our experimental design chapter, for us to draw a cause and effect conclusion, we need to have randomly assigned treatments, which we don't here. So we can't say that assigning this worker to the drive-through caused the decrease without randomly assigning certain fast food restaurants to have an extra worker and others not to. However, it is providing evidence that the proportion of people who have to wait too long is now less than 63%. So let's do one more example where we find a p-value. We'll skip the conditions for this one. A national study found that 76% of teenagers use Instagram. Joe believes the proportion is greater for students at his school. He tests the hypothesis, where the null hypothesis is that the proportion of students at his school using Instagram is the same as that national rate. The alternative is what he believes to be true, or suspects to be true, which in actuality that it's greater than 76%. He has a random sample of 50 students. He finds that 41 of them use Instagram. We'll start by finding the test statistic. So for this problem, we have our distribution, which is based on the null hypothesis. Our null hypothesis says that 76% of teens use Instagram. Joe believes that's larger. He ends up with a sample statistic based on his random sample of 50 students of 41 out of 50. The other thing that we need for this distribution is the standard deviation. So we're going to do sigma p hat radical PQ over N. Okay? Now remember, we're using the p of 0.76, not the p-hat. We find our test statistic, and they're just going to do this in one step here. So we have our p-hat minus the true proportion from our null hypothesis, and divide that by the standard deviation, which is given by that equation there. We get a z-score of 0.99. Now we can go ahead and put this on our normal curve. It's drawn here with the z-scores along the bottom. However, it would be the same if we had that 0.76 here and that 0.81 over here for our p-hat. Shaded to the right because our alternative hypothesis said that he believes it's greater than 76%. So this is giving us the direction of our shaded. All right, we looked that up in our yellow table. Remember to do 1 minus because this is a right-tailed test. We get a p-value of 0.1611. And because that's greater than the alpha level of 5%, we're going to fail to reject the null hypothesis. When we fail to reject, it means we have insufficient evidence that this is true. So we do not have convincing evidence that the proportion of all students at Joe's school who use Instagram is higher than the national rate of 76%. One important thing to understand is that in situations where we fail to reject the null hypothesis, like the last problem, we didn't have convincing evidence that the proportion of students at Joe's school who use Instagram is above 76%. However, that doesn't mean that the null hypothesis is true. We're never allowed to conclude that the null hypothesis is true, and the reasoning is somewhat logical. So his sample proportion is 81%. That's higher than the null hypothesis, which stated it was 76%. So there is some evidence to support that alternative hypothesis that it's actually greater than that. However, it's just not convincing evidence. It's kind of the equivalent of a not guilty verdict in a criminal trial. A defendant is never declared innocent. There just isn't enough proof of his guilt beyond a reasonable doubt. So we have some proof that the proportion is actually higher, but it's not enough for us to declare this null hypothesis guilty, all right, with evidence beyond a reasonable doubt.